Dear students, welcome for this AICT Prerana Great Training Program. I welcome you all today for the subject of computer networks. And in computer networks, we are going to discuss something about the topic of data link layer, and in that, we are going to see in detail our framing. Okay, hope you all enjoy this day today, since we are going to see some interesting topic data link layer. So let me go to the session. So as we all know, the data link layer, it is the second layer of the OSI model. And of course, the first layer is the physical layer. So physical layer leads with a representation of bits, how these bits are going to be transmitted from the source and destination to using different transmission medium, or what type of links we are going to use, and what type of topologies we are going to use for sending the data, as well as the different formats in which the data is going to be used, and the media that is going to use, for whether it can be a wired or wireless. All these things we have in detail, we have seen in physical link, which deals with how the bits are represented and how it is being sent from the source end to the destination end, using different topologies and links and all together. Okay, and now we are going to see something about the second layer, that is the data link layer, the very important layer, the second layer, because it is one of the complex layer, because it have the complicated functionalities and liabilities hidden in this data link layer, because it has this major role of hiding the details of the underlying hardware, that is the what is the hardware and what is the what we are going to just hide all those details, and it act like that, that it is as a medium for the communication. That is its responsibility. So it whatever the functionalities are underground using your hardware, it's been hidden, and it only provides its way for how the medium to communicate. So that is the main idea of this data link layer, and it's a great job this particular layer is doing, because it is the one which is get connected. Okay, the data link layer, it is get connected with two hosts directly for communication. Okay, data link layer, where the two hosts are get directly connected for communication. Okay, so it provides a point-to-point connection, or it can also provide a broadcast system of type of connection. And at the same link, whatever the link that we are going to use, because it is a point, because we are going to use the same link, because data link layer deals with connection between the two end to end, in the sense between the two end, between the two hosts only. Okay, so that is the main responsibility of this data link layer. And why this layer tends to be more complex, in the sense when it deals with dealing with multiple hosts on a single collision domain. So at that time only this particular, because if it is between two systems, then that's no problem. But if it has been get connected with multiple hosts on a single collision domain, then the complexity arises there. Okay, so here when talking about the responsibility of this data link layer, is converts this data stream to signals bit by bit and send that over the underlying hardware. So that is the main, as I said before, that is the main responsibility. Convert the signals bit by bit and then send to the over the underlying hardware. That is nothing but the physical layer. It sends the data to the physical layer for transmission. At the receiving end, what happens in the sense, the data link layer, it picks up the data from the hardware, which are in the form of electrical signals, and assembles them in a recognizable frame format and hands over to the upper layer. So that is the responsibility of the data link layer at the receiver end. Okay. So next we're talking about the this data link layer is basically, it has been divided into two sub layers. We can see this data link layer. Also, it is a second layer of the OSI model, and again this data link layer is divided into two sub layers. One is the logical link control, the upper layer, and the down below layer is the medium access control. So the logical link control, it deals with all the protocols that is needed for flow control and error control. Okay, that is control, that is done by the logical link control. And of course, we're talking about the media max control. So it deals with actual control of media, how the type of media what we are using, whether wired or wireless, and how the data is being transmitted, how in a controlled way. Okay, so that is the media access control. Okay, so these are the two different sub layers, the work responsibilities of the sub layers in the data link layer. Let me see a diagram how the flow of this data link layers. This is a communication of data link layer happens. Okay, so here this data link layer it actually it flows when you're talking about this flow of this data link layer. It flows from the Alice to Bob. At the same time here, from the data link layer from the Alice, it flows to the router, or because as I said, it is a second layer, right? So it flows from the data link layer from the Alice. The data is being sent to the next to the physical layer, and from the physical layer, it has to send to the receiver. Who is the receiver at the end? Is the Bob is the receiver. And intermediate, there are some different routers who's going to forward this particular whatever the media, whatever the data, what we are going to transmit. Okay, so different types of routers are the R2 and the R4 and R3 and R5 and R7. These are the different routers in between, which are it takes a responsibility of taking off this particular data link, I mean the component and the data, and then it transmit from one through different routers, and finally it reaches to the data link layer of the Bob. Okay, so the responsibility of this routers has been given. Okay, so with the router R1, R2, each and every routers are get connected in either it can be a switched WAN or LAN. Through internet, providing internet service providers, it is get connected, and all those things. Okay, there are different gateways. So in intermediate, there are various functionalities and components are working for this transmission of this data packet between the two Alice as well as the Bob. Okay, so this is a flow of how this data link layer goes. Okay, in short, let me see this. This is how the structural diagram of the flow of this, again the data link layer. Okay, so from the host H1 and to the host H2, how it is flow with help of this router R2, R4, and R3, how the data has been flowed. Okay, so in short, I'm delivering this to you. Okay, so here we are talking about only the second two layers. We are talking only the two layers, but at the host H1 as well as in the H2, all the layers, TCP/IP, talking about the TCP/IP, all the five layers, it deals with all the five layers: the application, transport, network, data link, as well as the physical layer and the TCP/IP protocol. Okay, in the, I mean the TCP/IP model. Okay, at the host H1, and of course when we see in the host H2, it also deals with all the five layers, that is application, transport, network, data link, and physical. And we are now dealing with the second layer, that is the data link layer. But when talking about the intermediate nodes between the H1 and the H2, that is the route, that is as we have something of router R2 and R4 and R3, and these are all the intermediate nodes. And when we're talking about these intermediate nodes, it deals only with only the three layers of the TCP, because that is the physical, data link, and the network. It doesn't bother about the other two layers because it is only used for the controlling purpose. That particular layers will be used only to control. That's it. Okay, but only the three layers are involved for the data transmission. That is the physical, data link, and the network. Regarding in the case of, I'm talking about this network. I mean the intermediate nodes. Okay, but the host node H1 and the host node H2, that is the destination, it deals with all the five layers. Okay. So now let us see the position of this data link layer. This is the position of this data link layer. Okay, so here what happened in the sense, the frames from the data links, this 2 and 3 is nothing but the 2 is the data link layer process that happens. Okay, this is a router. Okay, and the packets, the frames from the data link layer is sent to the respective routers through the incoming port, and the router will do the routing process, because it has, the router is the one that decides on which particular route that particular packet has to be transmitted, because it defines the finest route for the data transmission. Okay, whether they have to go to the left or right or straight or whatever it is, that is the decision taken by the router, and the routing process will happens. And with the help of this data link protocol, the router will forward the data packet to the next node, because data link layer deals with this direct link between the two set of devices, and directly it moves to the next node, again to the router, and from the router it directs to the respective device it wants to communicate. So this is a data link layer position. Okay, so next we are going to see the what are the services that is being provided by the data link layer, or we can say that the major functionality of this data link layer is talking about this framing, error control, and flow control. So these are the main functionality of the data link layer, or we can say the data link layer services. Okay, these are the important services in the data link layer. Okay, so talking about this framing. So framing is nothing but here what data link layer takes in the sense it takes the packet from the network layer and it encapsulates them into frames. That is how the frame came in data link layer. So the packet of the data network layer. So the data link layer on top of the data link layer is the network layer. So it gets the packet from the data link layer and it sends that particular packet to the before sending that particular packet to the physical layer, it will encapsulate that packet into a frame. Okay, then it sends each and every frame in the form of bit by bit on the hardware. On the hardware, in the sense, on the particular physical device, it will send that particular physical device, physical layer. It will send because physical layer deals with the different hardware for transmitting the data packets. Okay, so at what happens at the receiver end, the receiver and the data link layer, it picks up the data in the form of electrical signals from the physical layer and it will decapsulate that particular data into in the frame and send the packet to the respective upper layer, that is the network layer. So this is something about the framing. So the stream of bits will be broken down in the form of a discrete frames. Okay, so bits will be grouped together to form a frame. That's it. That's something about the frame. Next, error control. We all know there are various ways how errors occurs, the noise and the disturbances that cause while transmission of data packet, and that will be has to be controlled while transmitting the data, right? So how does the sender know that all packets are correctly received? So that is the main responsibility, and that is one of the responsibility of the data link. Whether the data packet that has been sent is whether it is reached without any malpractice or without any noise or without any disturbances or without any loss of signal or something like that. That is some we are regarding about the error control in data link service. And last one is the flow control. So flow control it deals with how the station on the same link may have different speed or capacity. Okay, so based on this here, the data link it ensures that flow control that enables that machine to exchange data on same speed. That is very important. That machine have to be exchange data on the same speed. Okay, so that is has to be that is a flow control. Okay, the flow of data has to be controlled. That is another responsibility of the data link layer. If there is a high data flow, if the sender is sending 5 megabits per second and receiving only 1 megabits per second, at one point of time, what happens? All the if a buffer capacity is very low and the buffer overflows and there will be loss of packet. So the capacity, the flow should be the speed of flow should be maintained between the sender and the receiver. Okay, if there is only one packet at a time being sent and receiver receives one packet at a time, then there will be no that particular losses there. So that has to be controlled. That is another responsibility of this data link layer. So these are the important services of this data link: framing, error control, and the flow control. Next, when talking about the framing, so in detail, we are going to see something about the framing in data link layer. So, okay, this is one of the important function of this data link layer because so here this why? Because it provides a way for the sender to transmit the data. So that is the important thing. So it provides the framing in a sense. It provides a way for the sender to transmit the data in the form of bits, so that the data are meaningful for the receiver to receive that particular data. Okay, so the data that is to be transmitted it should be meaningful, right? So that is something about the framing. So framing is a function of the data link layer that provides a way for the sender to transmit a set of bits that are meaningful to the receiver. So receiver has to receive the data in a meaningful way. Okay, so that is something very important about this framing. Okay, framing. This is one of the important functionality, of course, in the data link layer. The framing, this particular framing. Okay. So next, so here see this framing in the sense we have to the packet that is being received from the network layer has to be framed with a has to be framed. So this frame, there is a format of this particular frame. So this frame should have a header as well as the frame. It should have a proper payload field for holding the particular packet, and then you should have a frame trailer. So this is a format of framing. So we, as I said before, the data, what data link layer does in the sense it receives a packet from the network layer, it will encapsulate that particular packet and then into a frame, and then it will send the packet to the lower layer, that is the physical layer for the transmission, and at the receiver end, it will receive the particular data link, the packet, and then it will encapsulate that particular frame and receives the packet and pass to the next higher upper layer, that is the network layer. Okay, So that frame, that encapsulation and decapsulation is what is said to be the framing, where the packet, whatever the packet what we receive from data player is the data, that is packet nothing but the data what we are going to send, the message what we are going to send. It is the payload that is to be that is the payload part. Okay, that is the data part, and that particular data part is encapsulated with the frame header and a frame trailer. So frame header and frame trailer, you all know that. So the frame header. So what is a frame header in the sense? This frame header will contain the source address and the destination. The source is the alias and destination is the Bob, in the sense that the frame header will contain the source address as Bob, alias, and the destination address as the Bob. That is the frame header. Whereas the payload represents the data or the message what we're going to send. And finally, that is ended with something about the frame trailer, where it will have some certain bits for error correction and detection in case if there is any, because that is one of the responsibility of data link layer for error control, right? So for that, for error correction, if there is any errors has happened, and how to detect that particular error, and what and how way we can able to correct that particular error. So error correction, detection, and correction is done by means of this trailer part. That is the frame trailer. It takes that responsibility. Okay, so this is something about the framing of this data link layer. So let me see in detail about the parts of frame. So what is this parts of frame? As I said, frame header, it will contain the source and destination address, and table it nothing but the message what we are going to transmit. As well as the trailer, it contains error detection as well as error correction bit will be there in the trailer. And we also have something what is called to be as a flag. So flag, it marks the beginning and the end of the, because the frame that is to be transmitted, the receiver does not know what is the data and when the data are coming, and what is the starting of the data, and what is the ending of the data. So for each and every frame, to initiate or to say to the receiver that this is the starting position of the frame and this is the end of this particular frame, to initiate and to convey that information to the receiver. So each and every frame again is encapsulated with something of flag bit. The flag bit will indicate that this is the start of the frame, or the end flag, the frame, the after the framing, after the frame structure at the end, there is another flag bit to indicate this is the end of the frame. So each and every frame has its own flag at the top and as well as the bottom, and the top indicates that this is the starting of the frame, and the bottom indicates that this is the end of the frame. So it marks the beginning and the end of the frame. So that is the parts. The frame has these following parts. That is frame header, payload, trailer. Along with together, we have flag for to indicate that this is the beginning and the end of the frame. Okay. So next, when talking about this, what is the problem in framing? So there has been framing. We said that we have doing framing, and what is this problem in framing? Okay, we are encapsulating and we are giving frame header, frame trailer, the payload with along with the two flags. But what is this problem? So detecting the starting of the frame. We know that detecting the starting of the frame is done by means of a flag. So how to indicate that this is a frame is being started? So that is a good question. Okay, so how to, in the sense, only is nothing to worry about or nothing to think about, that the each and every frame has a flag at the top, at the first slot, as the first frame is nothing, when the first part of the frame is nothing but is a flag. That flag indicates that this is the starting of the frame, and the end of the frame, that is also another flag to indicate that this is the end of the frame. So this detecting the starting of the frame is done by means of a flag bit. And again, how does the station detect the frame? Okay, the station detects the frame in the stations. When it receives a flag, this flag indicates that, as I said, this is the start of the frame. By the flag, on receiving the first flag, it will indicate, to come to a conclusion that there is a frame is going to be received, which contains the frame header, the payload of the data, and the trailer, and that frame will be ended with the frame trailer, ended with another flag. Okay, so this is how station. So station, how does a station detect? In the sense, by the indication of the flag bit that is it is encapsulated at the starting of the frame, and at the same time, the last person that is detecting the end of the frame. How the frame is being detected that this is the end of the frame is nothing but this. Again, we are going to use another flag for indicating that this is the end of the frame. So this is, but due to some problems that has been occurred. So due to some problems, it has been this particular starting flag and the ending flag needed have to be embedded along with the frame. Okay, so to indicate that this is the starting of the frame and indicate that this is the end of the frame. Okay, so there are framings. We're talking about the frame. We have some different types of framing also, we have a fixed size of framing as well as we have a variable size of framing. By the term itself, fixed size, it indicates that the size is defined. It is not like there's a predefined size. It is not like that. So the size is not defined or it is default. So the size itself can be used as the delimiter. That is the fixed size framing. So fixed size framing in the sense here the size is being used as a delimiter. This is a format. This is for the data has to be transmitted. This is the bit, the prop bit. This is the header bit. This much is to be the trailer bit, and followed with this is the payload bit. So this is the delimiter has to be mentioned. That is the fixed framing. Whereas in the case of variable framing, in the sense here there is a need to define the end of the frame as well as the beginning of the frame, because variable size in the sense the frame size will be of any size. It can be of any size. There is a varied size of frames. Okay, so to indicate this varied size of frames, that we have, that should be a flag at the starting position of the frame, and there should be a flag at the ending position of the frame. We indicate this is the starting of the frame and this is the ending of the frame. Okay, so that is the variable size. And of course, in order to better identify the starting and the ending and the problems that arise in this variable size framing, they have some certain solutions to this, something like what is called to be as the character byte stuffing, and another one is the bit stuffing. Character or byte stuffing, another one is the bit stuffing. Okay, so what is this character or byte stuffing? We're talking about this. Okay, character or byte stuffing. This is very important. So we saw that this why we go for this particular topic, character or byte stuffing. In the sense, as I said, we are talking about this framing concept. In framing concept, we have a start frame and end frame indicated by means of a flag. So in a variable size, the size of the frame is not fixed. It is of varied size. Okay, it can be of 2 MB or 2 KB or any size, okay, any size frame, 1 MB frame or something like that. So, but not to indicate this is the starting of the frame and ending of the frame. As I said before, if we have a flag, if suppose the data that is to be transmitted have a symbol the same as that of the flag, how do the recipient come to know that this is the data, but this is not the indication that it is the end of the flag? I suppose you all understood the question what I asked. Okay, so please listen to it. The question here is, we all know that the frame is ended by means of giving the frame is ended by means of the flag bit. We all know that by means of flag bit, uh, the frame is, whether the frame is the beginning of the frame or whether the frame is the end of the frame. We all know. Okay, but my question here is, if suppose if the data that is to be transmitted, if it has a symbol a same as that of the flag bit, okay, a same as a flag bit, we have a symbol in the sense, how do the receiver comes to know that the data that is to be received is is actually the data, but it is not the indication that it is the end of the flag? And how the solution, and what is the solution now for this confusion to be taken place, and what is the solution? For that only we go for these two types, that is the character byte stuffing, and another one is the character bit stuffing. Okay, we have this character byte stuffing as well as the character bit stuffing. So this talking about this character byte stuffing, by the term itself, when talking about this character byte stuffing. Okay, so what is this character byte stuffing is, here, this particular it carries a 8-bit character from the coding system. Okay, 8-bit character. Okay, this character by oriented byte stuffing, it's going to carry a 8-bit header, 8-bit. I mean 8-bit characters from the coding system, and it has a header. You see the start frame delimiter. It has a header as well as it has a trailer. This particular character byte stuffing also has a trailer. So for the error correction as well as for the error detection, and in end of the frame is also indicated by means of the flag. So as you see in this diagram, we have a flag also to indicate that this is the end of the starting of the frame and this is the ending of the So we all know that. Okay. So because that is character oriented, it become popular because it uses the text transmission. It uses the text for the transmission in the data link layer. Okay. So and this flag can would be used or selected for any character, but not used for the text communication. Okay, the flag that we used to can be selected for any character, but not for the text communication. Because we also send other types of information such as a graph or audio as well as for video. So the question answer is asked bespoke. For example, if any pattern uses the same flag, would be a part of information. But if the receiver encounters this pattern as the middle of data, then it has to then it will is the middle of data, but it thinks that it has reached the end of the frame. So what is the solution? What is the problem? This particular problem, what is the solution? That is the question as I asked before. Okay, so we go for something what is called as byte stuffing. Was this byte stuffing or character stuffing was introduced in this character oriented framing. Okay, in this character oriented framing, we all know what is character oriented framing in the sense. Here it is going to use a 8-bit character for the framing structure, and it can be of mainly of text because it has been popular by using of text. At the same time, it can also able to store other types of information in the form of audio, video, or graph or something like that. Okay, so in order to understand and fix this problem, we go for something what is called as byte stuffing. So byte stuffing here, in the sense here we are going to use a single byte that is to be stuffed along with the data in transmission to indicate that this is not the end of the flag, but this is the information that is to be transmitted. Okay, in clear, when we see this diagram, for example, if we see the second the second row in this particular diagram, the frame sent. The frame sent is what is the frame sent? We have a flag which indicates that this is a starting of the flag, and there is a header, and followed with something. We have something what is called as escape, and another flag. We have another flag. What is a flag in between? Okay. So here, what is this meaning of this escape? In the sense, it indicates that this is a special byte. This escape is the special byte. What we are going to stuff. As I said, byte stuffing, it is going to type a byte. So what is the byte that is going to be stuffed in this? It is a special byte, right? So here it is going to use this escape character to be stuffed in front of the flag. In front of the flag. Okay. If suppose that this flag in between is going to be the information what we are going to send, but it is not represents the end of the frame, then that in previous to the previous of it, we have to stuff 8-bit character, a special character that is the escape. We have to give escape. Okay, so that has to be stuffed in previous to that of the flag. So when a receiver, when it going to receive this escape, when he receives this escape character, he comes to know that okay, there is an escape character, and the next byte is the information, but it is not the indication of any symbol to be ended or opened or something like that. So that is information known to the receiver. Okay, when he encounters escape, he comes to know that this next frame is the information that is to be transmitted. So from that, the next the one that is the flag, when he encounters the flag, the next thing, he knows that this is a type of information that is to be sent, but this is not the indication of the flag. Okay, this is something what is called as byte stuffing. So where we are going to stuff a byte in front of any message or information that is to be sent. If suppose, because we are stuffing escape symbol, right? If suppose if the escape is one type of information that is to be sent, escape itself is another one information. Apart of flag, escape is also there as an information to be sent in the sense. At that time, what we have to do in the sense, again, we have to, in front of escape, we have to stuff another escape. Okay, there is one escape, right? So in front of the information escape, we have to stuff the same the escape. So by means of stuffing this 8-bit character escape, again the receiver, when he firstly encounters the escape, and the first escape is encountered, it comes to know that the next next piece is the information that is to be transmitted, whether it can be an escape or whether it can be a flag. The next information is the next data is the information, but not the end of the frame or the starting of the frame. Okay, this is how we are going to implement this character or byte stuffing. This is how this is what is called as character byte stuffing. Okay, so normally in this particular sequences we found that such frames are two such characters are being popped, I mean has been stuffed, and it is being sent to the receiver. Okay, so this is something about the character byte stuffing. So this character byte stuffing, it uses only one byte um, for stuffing of the data. Okay, it uses only one byte. Next is something about we are going to see the bit stuffing. So what is this bit oriented? Normally we're talking about the bit stuffing. It happens in the bit oriented framing. Okay, in bit oriented framing here, the data part will be a sequence of bits to be interpreted by the upper layer. Okay, it will be in the form of the data bits of data that is interpreted in the form of upper layers. It can be of text or graphics or audio or video and so on. Okay, so there is a need frame to separate with another frame. So for that we have suffered with something what is called as a header and frame. Okay, so here in bit stuffing what we are saying is, here for example the header frame or the trailer frame is nothing but it is a 8-bit pattern flag. Okay, it is an 8-bit pattern flag. Okay, so what is this in the sense, if the same problem, if it is an 8-bit character like for example 0111 and again 111 followed with another 0, if it is an 8-bit pattern that is to be stuffed in the as a starting of the frame as well as at the ending of the frame. Okay, this flag bit is nothing but this 8-bit character is being stuffed. Okay, if suppose if again this 8-bit character has been used in middle of the payload as an indication that this is a message, so how to indicate to the receiver the next what is that is nothing but this is the end of the frame, but this is not the information that is to be sent. So how, because only receiver he knows that this is an end of the frame, the same problem, but how to convey to them? Again we have to insert another sequence here. Okay, so what is that sequence in the sense? For example, if the bit is here, that will be transmitted. For example, we are the end frame delimiter is nothing but if it is of 0 followed with the 6 ones and ended with another 0 in the sense. So what normally we do in the sense, if there are 6 ones, then what as a what bit stuffing in the sense we are going to stuff only one bit. So what we do in the sense, instead of 6 ones, here we are going to choose only 5 ones. Minus 1. 6 now, minus, if 6 now, we are going to minus 1. So what happened in the sense, we have five bits. Okay, so 5 ones consecutive. So we have to add a single zero, a single bit, zeros to be stuffed, bit stuff, that is a bit stuffing. Okay, we are going to stuff a single zero after the 5 consecutive ones. Okay, and then followed with the next data to be transmitted. This is the indication that this particular set of data, that is 0, the 41 and followed with the 0, this particular bit string is not end or starting of a frame, but this is the information that is to be sent. Okay, to give that particular information, we are going for this bit stuffing. That bit stuffing in the sense, if there is a 0 followed with the 6 characters of 1 and then ended with a 0, another 0 in the sense, what we do in the sense, if there is a 6 consecutive one, we are going to use only 5 consecutive ones. In the message, if there is only 5 consecutive one, and automatically we are going to insert a delimiter, that is the 0, and then it's followed by the remaining bit stream to be transmitted. Okay, so this is an example. See here in this diagram we see an example here. So what is that in the sense, here the actually the data to be sent from the upper layer is 000 and 6 1 and followed with 00 and again with 5 ones and then 0 1 000. So consequently, as I said, if it is 5 1, then we have to insert the 0. That is what the same thing. The same thing they are done here. See, there are two zeros, two bold zeros are there. So before that, we have 5 consecutive one. So if there is a 5 consecutive one, and if you have a bold 0 to be inserted, and then it indicates to the receiver that this frame is an information, but this is not the end of the frame, because the end of the frame is also using the same bit sequence 0 to 111 It's using the same thing. Okay, so that is something about the bit stuffing. Okay, So here we are going to add some extra 2 bits to the data that is to be transmitted, and the receiver will receive that particular data, and he will eliminate the type of bit that is to be inserted at the time of bit stuffing at sender. Okay, so this is something about the character byte stuffing as well as character bit stuffing. So let me see an example here. For an example, if data is 0, 111, followed with the 000, 111, 10, and we have an end delimiter as 0 111. So normally here the end delimiter is indicated as 0 111, and what is the bit stuffing we do here? So if the data is here, see, normally data we have normally have 0 111, 000, and 0. So we have to insert bit stuffing. So what we do in this is an end delimiter is also 0 111. So normally if it is a 111, then we have to insert 0 using double after double one. Okay, if there is a 111 as an end delimiter, then we have to stuff a bit 0 after double one. Okay, that is the concept. Okay, so that is what we have done here. See, in yellow color, the bolden 0 is nothing but the first bolden 0 is has been inserted after the double one, because we have 0 111 000. So now gradually what happened in the sense, now 0 111, once double one encounters, it automatically inserts a bit stuffing. A bit is being stuffed and followed with the remaining bits. Okay, if again there is another 111 is being encountered, and automatically after the double one it will insert another 0, it will proceed. This is something about the bit stuffing. The same in the second example, the data is double one, 000, and 1 1 1 0 0 1. Okay, and end delimiter we have 1 0 0 0, that is 1000. Okay, 1 0 0 0. So here 1 0 0 0, here we have 0 0 0 as the end delimiter. So normally from this we can say that if it is a 0 0 0, then we can choose only 2 0. Since it is 0, now the bit stuffing what we are going to stuff is it going to be 1. Okay, bit stuffing will be 1 here. Okay, so that is 1 in the sense after the 2 0 we are going to stuff 1. So that is, see in this example, let me see. So here 1 1 1 0 0, and we are stuffing 1 and followed with the remaining bits of characters that is to be stuffed. Okay, one because there is three zeros. Then when if 2 zeros is encountered, then we are going to insert one bit is going to be stuffed. That is 1. This is normally the example of a character stuffing as well as the bit stuffing. Okay. So this is a sample gate questions that has been asked. If a bit stuffing based framing protocol uses a 8-bit delimiter pattern of, this is a 8-bit delimiter pattern what we use. Okay, 0 111 111 0. The output will stream after stuffing. So after stuffing, we have got the output. They were asking what is the input. Okay, so here the output is 0. Because from this we come to a conclusions, because we know that bit stuffing, what is bit stuffing. So here actually we have consecutive in the delimiter, the end and the starting and the end delimiter has consequently we have some 6 ones. So normally what we do in the sense, the data bit, if it encounters 5 ones, then we have to insert 0. If there is 5 ones, we have to insert 0. Based on that particular concept, let me think of what would be the input here. So there should be some 5 ones. So here in this output we have 0, double one. After 5 1 we have a 0. So they have inserted 0 at starting itself after 5 1. So that 0 should not be there in the input stream. So we have to remove that 0. So 0, and what we should have in the sense 0 1 1 0 1. Okay, so what is that 101? Where it is 0 1 101, and of course it is at the option B. Option B have that particular thing, and of course that is the input. Okay, input stream. So option B is the answer. It is very simple. It is very easy and simple question. If you know what is bit stuffing and byte stuffing, you can able to easily answer these questions. This is one of the sample question in bit stuffing. Okay, and that is another question. Data link protocol. The frame delimiter flag is, now it is 0 111. So if it is 111, what does it mean? That's triple. There is 111. So we have to stuff a bit after double one. Okay, so 1 1. Then we have to insert 0 and follow with another 1. Okay, that is the same. That is the concept. So that is to be followed. Okay. So here again we have assuming that the bit stream is employed. The transmitter sends the data sequence as 0, 111, 111, 0. So what is the output of this particular data? Here we are asking the output. What is the output? Transmitter sends this particular data, and what is the output? So from this, we know that this is a 111. The delimiter is 111. So we have to insert 0 after 11. So what will be the answer? 0, 11. We are in, that is a 111, right? So 0. Once 11 is encountered, then we have to insert 0. So normally, what is the choice? 0, 11, 0, 1. Where it is 0, 11, 0, 1. Yes, we have the option of 0. 1101 01101. We have so the A and B option. Okay, and B option 0, then 0 111 011. So what is the output, right? So 0 110. So option D. So we can go with option A, B, and D. And again, that is double one is encountered. Again, there is a double one is encountered, and that should be followed with 0 0, and last 1100, where it ends with 1100. A does not have 1100. Not ended with 0110, and B is also not ended with 01100, but D option ended with 01100. So we can conclude that the option D is the correct one. Okay. Next, we're talking about this. The next sample question. Consider a parity check code with 3 data bits and 4 parity bits. Okay, this is a parity check code. Okay. And let me talk this particular question after learning to the parity check. Okay. Uh, let me go with another slide. Okay. Okay. Let me see another problem. A bit stuffing. It is based on framing protocol. Uses a 8-bit delimiter. The same thing. The output frame is this, and of course we have the same thing. And what is the output for this? Nothing but. So from this we come to know that the output is option B. Okay, 0. So okay, we all know, we have discussed this because we have 6 1, and of course after 5 1 there should be, if there is a 0, then the output is, and what will be the input. We have discussed this first. Okay, thank you. And so these are some of the samples. It's very easy and to solve this particular bit stuffing and byte stuffing if you are very clear. Okay, so next we go with the topic of error detection and correction. Okay, so we are today we are going to see only error detection in the data link layer. Okay, so normally we know that when the receiver receives this information, it will not match with the sender's information. Why? Because at the time of transmission, the digital signal that is being transmitted, it suffers from noise. So that what happens then, there will be some errors will be introduced in the binary bits that is traveling from the sender and receiver. So now, of course, there will be some noise because it has to travel very long distance, right? So there will be some errors will be happening. Okay. So what is this error? What way? Because all signals are data are transmitted in the form of signals as zeros and ones. Normally, it is nothing but there will be the zeros will be changed to 1, or 1 will be changed to 0. That is normally the noise that causes the disturbances in the data to be transmitted. So that is why the receiver, when he receives the data, he finds that the data that he received is not matched up with the data that is sent by the sender. Because due to this changes of bits like 0 to 1 or 1 to 0, this is the representation of noise. So there is a need for detecting this error. Okay, we for that we go for a special error detecting code, where what is this basic approach of this error detecting code? In the sense, it uses a redundancy bits, or we call as extra bits. It uses an redundancy bits to check whether there is an error or not. That is the error detecting procedure that happens normally. Okay, so here we are going to use some redundant bits, or we can say extra bits, for as a basic approach to detect whether there is the message or the data that is to be transmitted has error or not. Okay, so what are the popular techniques that we used in this error detection? Some of the popular bits, popular this in the sense, simple parity check, two-dimensional parity check, checksum, and CRC, cycle redundancy code. So these are some of the popular techniques that's been used for error detection. So as I said before, error detection, this is detecting whether there is any error in the data that is to be sent. Okay. So normally we can also go for correction. Okay, where once error is detected, we can go for correction. So it will happen. If it is detected, we will go for correction, because normally, as I said, errors are nothing but ones will be sent to 0 and 0 will be transferred to 1. So normally we go to, and this error correction will happen only for 3 bit, but not more than that. Okay, so that is the error correction. So let first we study something about the error detection in data link layer. So let me see the each and every techniques, that is starting from the simple parity to CRC. Okay. So first is the simple parity check. This is very the simple basic approach, the simple parity check in the sense, because the block of data that is to be sent by the source, or we have to check a bit, or we are also we call as a parity bit is being generated. Okay, so each along with each of the data that is to be sent by the sender, and that parity bit is added along with the source data that is to be transmitted. That is, as I said, no, we have to, error detection happens by only by using some extra bit or redundancy bit has to be added. Okay, so here we are going to add a single bit. That single bit only what we call to be as a parity bit. Okay, as in order to check whether there is any error detection happen, not to detect whether there is error happens in the data that is being transmitted. Okay, so here we have a condition how way that the parity bit is added. Okay, so here what it says in the sense, the data that is to be transmitted, if there is a even number of ones, if it has an even number of ones is there in the sense, then we have to add 0. Okay, if there is even number of ones, then we have to add 0 as a parity bit, that is the extra bit is to be added. If there is odd number of ones, then we have to add 1. Okay, if there is even number of ones, then we have to add 0 as a parity bit. If there is odd number of ones, then we have to add 1 as a parity bit. So by conclusion, what does it mean in this sense? The source data that is to be transmitted, you should contain even number of ones. We should not have any odd number of ones. There should be some even number of ones. That is a simple logic here. Okay, so that is the simple parity. The simple parity check, we are only going to add only one bit, and that one bit is nothing but either it can be 0 or 1. So when a 0 is added, in the sense, if the data bit has even number of ones, then we have to add 0. If the data bit has odd number of ones, then we have to add 1. This is a simple parity check. Okay, so let me see with this example. So this is an you can see the example on screen here. Okay, this is an example. It has been clearly said that we are sending 1 0 0 0 1 1 at the center side. Okay, so what happened in the sense, we have to calculate the parity bit. We have to compute the parity bit. So this sender has sent 1 0 0 0 1 1. So we have odd number of 1. So we have odd number of 1 in the sense. Then we have to make it to even number of 1. So we have to add 1 extra bit, that is 1 bit. So 1 as added, because we have odd number of ones, we have to add 1 as a parity bit is added, and it will be sent. Okay, through transmission media, it will be sent to the receiver. What receiver will do in the sense, he will receive 1 0 0 0 1 1 and 1 extra 1, the parity bit. Along with the parity bit only, it will be sent. Okay, so the receiver receives this parity bit. He will compute. Okay, he will compute whether there is any even number of ones or whether there is any odd number of ones. So he will check at the receiver side. He will check. Okay, if it has even number of ones, then it is come to a conclusion that, okay, he will accept the data. Then if he has some odd number of ones, then he will come to a conclusion that that error is being detected and it has to be analyzed and it has to be corrected. Okay, this is a simple parity check. So that the receive, when he receives, he should detect, because as I said, noise is nothing but a single bit will be changed to 0 or 1. That's it. That's we call to be as a single bit error or burst bit error. That happens. Okay, so this possible only for single bit error. If any even number of if there is only even number of ones, that's no problem. If there is any odd number of ones, then the particular data bit will be rejected. Okay, this is a simple parity check code for detecting the errors. Next, we're talking about is the two-dimensional parity check. So this is another very simple concept. This is a two-dimensional parity check bit, because it is calculated for each and every row and as well as for the each and every column. The parity bit to be inserted is checked for each and every row as well as each and every column, and these parity bits are sent along with the data to the receiver, and the receiver at the other end, he will compare the parity bits compare parity with the parity bit, and he calculates it, and he will finally he will come to a conclusion whether the bit is been, whether there is any the error, or he will check come to a conclusion. He will detect, or if he finds out if there is any error, or if there is that he'll accept it. If there is any error, he will reject the data. If there is no error, he will accept that particular data. This is a two-dimensional parity check. So from this diagram, we come to know that the original data that is to be transmitted, this is the original data. Actually, we have some 4 blocks of data to be transmitted. So like 100, double one, 001, and triple one, 00010, and double one, 100, 100, and this is a simple. This is a data that is to be transmitted. Okay, so normally what happens in the sense, for each and every row, so it is to be represented in the form of a column. Okay, row column wise, we have to insert that particular block of data, and for each and every row and for each and every column, we have to compute. Okay, for each and every row and for each and every column. For example, if you take the first row, 100, 1100, we have even number of ones, so we have to include 0. The row parity is 0. And the second row, we have even number of ones, so we have to insert 0. Next also, we have even number of 1, 0. Next also, we have even number of 1, we have 0. When you take the column, it is found that first column have odd number of 1, so we have to include 1. Next column, we have odd number, that is only 1, 1, so we have to include 1. And the next column, we have even number of ones, then 0. Next is odd number of 1, 1. Next is also odd number of 1, that is 1. Next is even number of 1, then we have to including 0. And the last one is also even number of odd number of 1, we are adding 1. Okay, so this is the case. So, and along with this, we are going to send the data. See, at last, we are sending the data along with the parity bit, and that parity bit is included. See, for example, this 8-bit is being presented as here see 9-bit. So the 8-bit of source data is sent along with the parity bit as 9-bit. So 9-bit is being sent for each and every block, and totally at the source there is only 4 blocks. But while we are sending, we are sending 5 blocks of data. Okay, so this is the parity bits that is being included. So we have in simple parity check, we have included only one parity, but here including some several parity bits are included, and it is being sent to the receiver. And the receiver, he will arrange the row column wise, and he will come sort it out the parity bit. And finally, if he finds that there is that should be some even number of ones and odd number of ones. If it encounters there is any odd number of one, from that he will come to a conclusion or detect that there is an error happens, and he will take on the next step for error correction. Okay, so this is the concept of two-dimensional parity check. Okay, so very simple concept. And next is the checksum, finding the checksum, and then we are calculating it out. Okay, this is another very simple and concept of finding the checksum. A little bit complex, or not much complex. We have to find, because most probably in data in data field in this network, most probably in all the frame formats, we have a checksum at the other end, because checksum, it is for error detection and correction most probably. So it is very important to know how this checksum is calculated and what is a checksum to be added along with each and every frame. That is very important. Most of the data that is to be transmitted in this frame format, the last frame format is the checksum. In all the wireless wired data for data frame that is to be transmitted for, it is being used for communication. The frame forming its frame format itself, we have a special byte of data for checksum. Okay, we have a special field for the checksum. Okay, so it is very important to know how this checksum is calculated and how it is being used for error detection. Okay, so that is another important concept in this checksum. So what we do in this checksum, it's very simple. What we do in this checksum. So in this checksum, the data is divided into k segments, and each with m bits. So here we divide that into k segments, each with m bits. So totally k segments. So totally how many segments here is? We have 4 segments, and m bits nothing but the 8 bits. 8 bits are transmitted. So there should be some k segments and m bits. K is the how many number of blocks we are going to use, and bits, m bits represents how many number of bits is representing each and every block. Okay, in the center side, what we are going to, in the sense, we have to the segments are all is added using the ones complement, using ones complement addition. We are going to perform ones complement addition arithmetic operation, ones complement arithmetic operation at the center side of all the blocks of data. Yeah, for all the blocks of data, we are going to perform ones complement arithmetic addition, and after that, finally we get a result, right? So that result is complemented, and the complemented value only what we call to be at the checksum. That is the checksum value. That is the final checksum value what we get. Okay. So what we do in the sense that all these four blocks of data are added using one's complement arithmetic addition, and finally we'll receive a sum, receive an answer. That answer is complemented again, and once it's complemented, the complemented answer is what is called to be the checksum, and that checksum is included along with this blocks of data, and that will be sent to the receiver. And what receiver he is going, because here there is a four block of data has been sent, and along with the checksum it becomes five blocks of data. So these five blocks of data will be sent to the receiver, and what the receiver will do with all these five blocks of data, and again he will perform this once complement arithmetic operation, and finally the result we get, if he complements the result, if he complement the result, if all the bits are zero, then it will come to a conclusion that the bits that is being received are clear bits with no error. If any one is being find it out, then it encountered it, then it represents that the bits that is to be transmitted, that the data that is transmitted is as an error in the data. Okay, the error is that there is a disturbance in this data that is to be received. So this is how the checksum is calculated, is inserted, and it is best way of using for error detection and error correction. Okay, very simple and very easy concept, and most probably in all frame formats and all technologies, we are in a frame format. We have this checksum value for error detection and correction. Okay. So what is this checksum? Let me see an example here. Okay. So from this example, it is going to we you know you'll come to know clearly. Okay. So what we do in the sense 100 double one double zero is the first block, and we have all these blocks. Okay. So I mean, 100 double one double zero one. Okay, we have all the what is center side in the sense we are going to do addition. All the blocks have been added once complement addition. So for example, if you take 1 and 2, first two blocks, 100 11001 and triple zero 1 0. If we go on with addition, once complement addition, 10 is 1, 01 is 1, 1 1 1 1 1. Last 1 1 will give you 1 0. Okay, this 1 0 is 1 1 plus 1 is 2, 2 is finally is 1 0. So that 1, and that 1 we have a reminder, this carryover 1 in the sense the carryover 1 is also added up, and again we'll get a value of 0 double one double one one double zero. Okay, and that only value will be added with the third block. Okay, again we go for this at normal addition. When we do with the normal once complement arithmetic addition, there is no carry out. So since there is no carry out, directly we can include the fourth block and we add it. So once we add a 0 plus 1 1 1 0 plus 0 0 0 plus 0 1 plus 0 is 1 1, and finally 1 plus 1, again we have a 1 plus 1 is 1 0. Once again there is a carry of 1, and that 1 is also added, and finally we get a sum result as 0 0 1 double 0 1 0 1. And what we do in the sense, after adding all these four blocks of data, the sum value has to be complemented. Complemented in the sense zeros will be converted to 1 and ones will be converted to 0. So from this, what we get, what is the final answer we'll get in the sense double one, 0, double one, 0, 1, 0. So this is a checksum value. This value is a checksum, and that will be included along with the data block, and it will be sent to the receiver as a fifth block. This is can consider as a fifth block, and it will be sent to the receiver. What receiver will do in the sense, again he will do all this type of addition, the same once complement arithmetic addition with all these five blocks, and finally he receives some value of the 1 1 1 1 1 1 1. Okay, when we do his complement, he will receive 0 0 0 0 0. So when all the bits are zeros, it comes to a conclusion that this particular data block is pure data with no error, and he will accept that particular data. Otherwise, he will reject that particular data. This is the value of finding the checksum for used for error detection and error detection. Okay. So next, cyclic redundancy check. So what is this cyclic redundancy check? When talking about this is another CRC. This is another very important, most probably in wireless communication. You can see this CRC code. Okay, cyclic redundancy check code. Okay, so this is not as that of the checksum like that where we use like once complement addition and stuff. Okay, that is not the case. Here we go for binary division. In cyclic redundancy check, we go for a binary division. So where a sequence of redundant bits called cyclic redundancy check bits are appended to the end of the data. Okay. So as I said, we are going to append here something of some CRC value. Okay, well, how do we get the CRC value? In essence, by doing some binary division, we'll get the CRC value, and that CRC value will be appended along with the data, and that will be sent along from the sender's side to the receiver side. Okay, so what happens at the receiver side? What they will do then is they will get the incoming data, and again they will do the binary division with the number, with the same number what they done at the sender. The sender, the quotient value is going to be the same at both ends. Okay, so the same quotient value, they will do again the same division. If the if there is no reminder, if the reminder is 0, there is no reminder, then it comes to conclusion that the data unit what we receive is correct and there is no error. So we can able to accept the data. If there is any change in the, if there is any reminder, then it comes to conclusion the data bit is being corrected. Okay. So the reminder is the one which indicates that whether the data that is to be transmitted is damaged or not, or whether it is to be accepted or rejected. The final, after performing binary division, the result, that the reminder, that is the one that is going to give you at the sender's, at the receiver side. Okay, at the sender side, the reminder what we get is the nothing but the checksum value, that I mean the parity value, parity bit value or the redundant value that will be added along to the source, and it will be sent. Okay, so this is a simple logic. The diagram, what I've explained right now has been explained in the form of a diagram CRC. Let me see this with the little bit within a form of example. Okay, in the form of an example, let me see this what actually this CRC cycle redundancy check code is doing this. Okay, so here in CRC, as I said before, here so the checksum value, I mean the quotient, what we use is nothing but it is 1001 is the CRC generator, or the CRC generator is the device what we are going to use for divide this particular, the source original message, that is 101 double zero double zero. That particular message will be divided by means of this CRC generator 1001. We have to divide it. Okay, so normally what does it mean in the sense, so we are, before doing any addition, I mean before doing any binary division, the original value has to be appended with some value. So what value to be appended in the sense, for example, if the CRC generated is 4-bit, then for example if this n bit, then we have to append n minus 1 bit. That is a concept, so it has been given here. If the CRC generated is n bit, then we have to append with n minus 1. So in this case we have a CRC generator of 4-bit, so we have to append 3-bit. And what are the 3 bits we have to append in the sense? At first we have to append 0 0. Initially we are going to append 0 0 0 at the end of this particular bit. Okay, so we are going to insert 0 0 0. So 1001 is divided with 101 double 0 double 0 double 0 0. Okay, we are going to form the binary division. Okay, so when we perform this binary division, we will be getting the result as, finally what is the result as 0 0 double 1. Okay, so we are going to include only 3 bits. Okay, very important, because as I said, if the CRC generator is 4, then we have to get only 3. So the last 3 bit alone is being included. That is 0 1 1 is included along with the message, and that is appended along with the message of 101 double 0 double 0 is appended with 011, and that data will be sent to the receiver. What receiver will do? Again, the receiver at the end, he will perform the same division with the same divisor value, that is 1001, and finally he'll get a reminder of 0. That it should be no reminder as 0. If he gets a reminder of 0, then from this we come to a conclusion that the binary bit, that the data that is to be received is a pure data with no error. Otherwise, the data will be rejected. If otherwise, the data will be accepted. If it is by no reminder, then the data will be accepted. Otherwise, it will be rejected. So this is in the case of CRC, cyclic redundancy check. This is very, very important. As I said, the next, that's the checksum as well as the CRC, because most probably in most data frame format, we have the CRC or the checksum. Or to find out for error detection purposes, we have this, because normally we know that the data linker, that is the data that is to be transmitted from one end to other end, there is a possibility that errors occurs and noise occurs, and automatically the data that is to be transmitted will get corrupted and in another format. Okay, I'll receive in another format. So There is a responsibility for the data link layer to find out this error, and it has to make the responsibility to control this error. So that is why we are seeing this error correction topic in this particular data link layer. So these are the techniques what we use. That is the simple parity check, the simple parity two-dimensional parity check, as well as the checksum and the CRC. These are the different techniques that is being used in this error detection. So these are see, okay. So this is something about, let me see some discuss about some gate question. Okay. Previously also we have seen some gate question regarding to parity bit. We have, that is a gate questions has been previously we encountered that. Consider parity check code with the 3 data bits and 4 parity check bit. Okay, 3 data bit, as well as we have a 4 parity, 3 data bit and 4 parity check bits. Key of the codes are these are the 3 of the codes. Which of the following are also code word? In this, we have to find out which one is the fourth code word, because we are saying that we are sending 3 data bit and fourth is the parity check bit. Okay, so they have mentioned the 3, and what is the fourth one? Okay, what is the possibility? The fourth bit is possible. So like, we know that how to find the parity check. Like we have 3 bits, so we have to do that two-dimensional parity bit check correction. Parity bit we have to perform it, and finally we have to find out the fourth code word. I will be find it out. Okay, so from this, either it is 1 and 3 or 1, 2 and 3. So by performing some operation, so better if you have time, we can do this. Okay, let me you can do this, you can try it on. Students, I ask you to try this. You try, you can say me the answer now. 0, 0. You can do the simple parity check. Okay. I mean, the two-dimensional parity check. As I said, we have to represent the form of rows and columns. Row wise, in column wise, we have to include. And see, when we do this, we'll get what? Okay. So yes, it's actually when we do 0, 0, 1, 1, 1, and when we do this operation, answer A, that would be the best answer, because 1 and 3, that is either can we have 3 or uh, either can be of 1 by performing this operation. Either we, if we do in one way, we get 1, and if we do other way, we'll be getting 3, and both are the correct answer for this particular question. Okay. Let g of x be the generator of polynomial uses in for CRC. For CRC, what is the condition that should be satisfied by g of x to detect odd number of bits in error? So we have to detect odd number of bits. What is the condition to be need? So let g of x contains more than g of x should contain more than 2 terms, or g of x does not divide with this particular value for any k and not exceeding the frame length, or 1 plus x is a factor of g of x, or g of x has an odd number of terms. So normally by term it is, we know that 1 plus x is always is a factor for g of x. So this is a normal factor, that is we all know, that is a general format that we all know that. So the answer for this question is almost, it is the 3. 1 plus x is always is a factor of g of x, and it has been proved also. Okay. So next, an error correcting code has the following code word. So what is the number of maximum number of bits errors that can be corrected? As I said before, the error correction maximum number of bit error can be corrected, and this is only 3 bit. Okay, I have said this in the class also. Okay, okay. The maximum error bit we have corrected is only 3 bits. It's not more than that. We can correct 1 bit, 2 bit, as well as up to the 3 bit we can correct, not more than. Otherwise, we have to resend the same data. That is the only possibility. If suppose if there is more than 3 bit, there is any change in a particular set of block, A to block, then we have to resend the data. Okay. Last question. So here we have a checksum value has been given of 16-bit segment. Okay. So what is the checksum value? Okay. So what would be the checksum value for this particular? So we have to normally we have to calculate. I have sent you the formula. What is the form step that has to be applied for this above discussion now to get the checksum value? So we have to try the value, and it has been found that answer C would be the correct value, because we know how to find the checksum value. So what is how to find the checksum value? We have to add all these, and once arithmetic operation, and finally the result will be complemented, and we're getting the checksum. So what is the checksum value for this of 16-bit segment? So it's very simple. So normally you just do this operation. We have only 2 segment, right? So add these 2 segment. When we add these 2 segment and we complement, we'll be getting the, the correct answer. Okay. So normally if you take 1 plus 1 is 1, 0. and 10 again. Two, so last two zeros are there, so we have to do when we complement 1 1, so we have option. Let me take the option C is the correct answer, last bit. Okay, so from, because it is better if we by this by looking on this, if we perform this addition for the last 4 bit, we'll get the answer by performing. It is not that by looking onto itself we can see, we can check, we can do the operation. We can do the once complement arithmetic operation for the last 4 bit, and if we complement, we'll be get the answer. Okay, so it is easily by this way seeing this, we know that the answer C is the correct answer. Last 4 bit, you would be getting like 1110, and that is the answer. In the answer C, the last 4 bit is 1110 we got. So of course that is the answer. Answer C is the right answer. Okay. So I hope I have discussed more about this particular data link layer concept, as well as this framing. What is the concept, different framings we do, like fixed framing and variable size framing, and what is the character byte stuffing and bit stuffing, and what is the responsibility, and how, when we have to do bit stuffing, and all those things. And we have discussed with some of the gate questions, as well as where we go with the concept of error correct detecting and various editing techniques like parity, two-dimensional checksum and CRC. We have also found solved kind of various problems. Also, we have found we have learned. Okay, I hope you all from this topic you have gained some knowledge on what is framing and error detection, and you can able to attend some of the gate questions from this topic. I hope you all know, because the most probably the gate questions has been given and has been said to you how to solve. Okay, if you have clearly listened to this, and then it will be very easy for you to attend some of the gate questions from these topics. So thank you, or do well, all the best. So regarding to this topic I'm talking about, so thank you for listening. Thank you for the session. So I'm going to wind up the session. So let me meet in the next class for the same data link layer in MAC. Okay, so medium access control. So let me see in this particular topic. We see the next class. Okay, thank you very much.